Whenever we talked about memory, I said that there were a number of inputs. So you had a bunch of address lines, A0, A1, A2, all the way down to like AN-1. And you had D0 to D7. And then you had this chip select, this read bar, and the W bar. Most all of these inputs to the memory are actually coming from the processor in order to control the interaction with the memory. The only thing that's two directions or bidirectional are the data lines. And so the process, once again, went something like this. In order for the processor to read data out of the memory device, it needs to have the chip select low, it needs to have read low, write high, it needs to have the appropriate address values or bits put on these address lines, and then the memory device is going to send data on the data lines in order for the processor to read it. In order for the processor to write data, what it has to do is have chip select low, read bar high, W bar low. That will set up the bus so that the processor, so that the memory device is going to accept something to be stored, the appropriate address on the address lines, and then the data lines to be set in order for them to store a value to the memory device. Now, I don't know if you've covered this in like 1400 or any other computer computer class, but reliability is really important, very important. Okay. You know, not just for like systems where, you know, Amazon Cloud or you know, a database system that an employee database system for a business, or, you know, the space shuttle or whatever it is, but also reliability is kind of important for a device sitting on your desk. And one of the things that makes reliability incredibly low is an increased number of connections. The more pins you've got, the less reliable the system is going to be. The more interfaces between devices, the more wires that are running between devices, lower your reliability is going to be. In addition, as we start to get devices that are smaller and smaller and smaller, the more connections we've got, the larger the chip has to be in order to support all those connections, and the more board space you've got to take up. In addition, chips that have more pins also are more expensive, because that's one of the high cost portions of manufacturing ICs, is actually connecting the signals that are on the silicon to the outside world. And so one of the things that they do is they actually divide the addresses in half. So you've got some point at which you have like a low half of the address and a high half of the address. The high half of the address and the low half of the address, high half is usually referred to as a row, and the low half is usually described as a column. Now, does anybody not have the handout from last week? You know, I've got a few left up here. Did you not have it because you lost it, forgot it? Now, unfortunately, I've drawn this kind of upside down. The column is usually referred to as the low half. So if you look at these address lines, you're starting at A0 going up to some midpoint. And then the row is usually referred to as the high half. And what we can do then is add two more control signals. And when you look at what's coming from the processor, the interface to the memory, there's actually only one set of connections, one set of pins for both that are shared for both the row and the column. And so in essence, these upper bits of the row, they actually map to the same physical pins. And you've got to have a signal, or two signals in this case, that identify whether we're looking at a column or a row for that same set of pins. This drawing is a little bit misleading, so maybe what we'll do is we'll go ahead and open up that handout.
If you look at the number of address lines, and in fact, there's a little hypothetical example up here. If we look at the number of pins that are required in order to address a memory location, if I've got n address lines, then that means I can have at most 2 to the n memory locations, right? Well, the problem is that the unreliability in any system tends to center around the number of physical connections we've got. Also, the number of physical connections increases the size of our devices. The number of physical connections also increases the amount of room it takes on a circuit board. There's a number of issues. So what we want to do is reduce that number of pins as much as we can. Well, there's a little bit of a diagram down here. In this worksheet, and there's a couple of things that I need to talk about first before we get to too much detail on this diagram. But notice that for this particular example, I have 10 address lines. Well, those 10 address lines, for a period of time, they contain a row address. And so notice these address lines go both to the row address buffer and the column address buffer. So for a period of time, they have a row address, and that row address goes into, don't worry about this mux yet, that row address gets passed through to a row decoder that selects one row out of this memory device, okay? And since there are 10, or excuse me, there are not 10 address lines, there are 11 address lines here going from A0 up to A10. Well, 2 to the 11th is equal to 2 to the 1 times 2 to the 10th, which is equal to 2 times 1K. So there are 2K rows. Then we change the values that are on these address lines so that it now contains a column address, and then that column address goes into the column decoder, and the column decoder selects one column out of our once again we've got 11 address lines, so now we have 2048 or 2K columns. And then where the two intersect, that's the memory location that we are looking for. Now, when we come back up here to look at this weird little diagram I've drawn, another way of looking at it is that first we select a row, then we select a column, and where the two intersect, there's basically bits. And those bits, each one stored in a capacitor, will contain the value that we need to return to the processor or that need to be updated if the processor is writing data. The problem is that by doing this, we have now created this three-step process. Step 1, give the upper half of the address. Step 2, give the lower half of the address, and then retrieve the data. And by the way, this timing is set up with these signals. We have these two signals. One of them is called RAS, and that is a row address select, and that's the one that goes active whenever we're trying to select the row. And then we have CAS, which is a column address select, which goes active whenever we're trying to identify the column. Notice that they're active low. In this diagram, both of these signals have bars over the top of them. So those are active low signals. So the process goes something like this. Assert or set the value for the upper half of the address, the row, strobe RAS. Then whenever that's been on there long enough for the memory to capture it, then put the low half of the address, the column, strobe CAS, and that will get the DRAM to identify the column, and it can then either return or write to the data that we're looking for. Now, the problem with that amount of time is, well, the bottleneck in any system seems to be how fast we can access things from memory. We're going to talk about trying to overcome that whenever we talk about multi-level memories, specifically cache memories. But one of the things that we try to do in terms of speeding things up is kind of change around how the row and column is given to the memory. One of the first attempts at changing this or improving the performance is fast page mode. Now, or FPM memory. Now, one of the principles that we are going to study, especially when we get into caches, is the principle of locality. Writing on this surface is not exactly making my handwriting any better than it was, huh? Principle of locality. And the principle of locality has 2 points, and we're going to get into these whenever we start talking about caches. The first point is that if I access anything, either an instruction or data, it is highly likely that I'm going to access it again. Think about a for loop. If I'm executing the code in a for loop, if I execute one of those instructions, let's say it's a for loop that goes from 1 to 10, I'm going to access that instruction 10 times. So the first time I access it, it's a really high chance that I'm going to access it again. When it comes to fast page mode, however, the second part of the principle of locality comes into play. And that second part says that if I access one instruction or piece of data, it is highly likely that I'm going to access its neighbors soon too. Let's go back to that for loop. If I execute the first instruction in that for loop, then it is very likely that I'm going to be executing the next instruction. In addition, whenever I declare variables, whenever I access one of the variables, it's highly likely that the variables that are declared near it are going to be accessed soon too. So by doing that, what we can do is we can set the high half, send the high half of the address, the row address, to our memory, and they then say, can you hold on to that for a moment, because I'm going to ask you to reference it again. And so that high address is held, and then what I'm going to do, and that's done, remember, with the RAS signal, I'm not going to update that. What I'm going to do is just keep giving you low addresses, the low half, that are accessed with CAS, right? And by doing that, what I've done is, well, let's see here. I've got 1, 2, 3, 4 bits of data that I'm accessing. If I did that here, like I'm doing up on the top part of this sheet, I would need to give it the high half, the low half, get the data. And then the high half, the low half, and get the data. Do that 4 times, and if we refer to each one of these periods here as a memory cycle, then what it would take is, to get these 4 pieces of data, it would take 4 times 3 memory cycles, or 12 memory cycles. All right, and that's with no FPM. But if we have FPM, in other words, this fast page mode, where I give it just the row once, but then give it column, 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 and get the data, how many memory cycles does it take now? Well, it takes 1, 2, 3, 4, 5, 6, 7, 8, 9. It takes 9 memory cycles. All right. And that's quite a savings. I mean, you're looking at 2/3 of the, or excuse me, 3/4 of the it takes 75% of the time that it would have if we did not have FPM. Now, this will speed things up significantly, and in fact, we'll get a little bit more of an improvement the more the more bytes of memory we can pull from memory in a row. Okay. Now, that's good, but remember, the principle of locality has this, especially whenever it comes to code, has kind of a sub principle, and that principle is referred to as sequential locality, and that particularly applies to our code. Whenever I execute the first instruction, chances are really good I'm going to execute the next instruction in memory, and then I'm going to execute the next instruction in memory. Well, that gives us an additional method of accessing data, and this is called EDO, or Extended Data Out. In this case, what we do is we give it the row address, right? So we strobe ras to say that we've got the row address. Then we give the column address, and we strobe cas in order to get the column address identified. And then we just assume, okay, we're going to get the first instruction, the next instruction, the next instruction, the next instruction in order in memory. All right. And what this does is now with EDO memory, what we've got is 1, 2, 3, 4, 5, 6 memory cycles. In fact, at this point, with just retrieving 4 bytes, we've cut the access time in half. We're taking only half the memory cycles. Well, think about it this way. If I have 1,000 of these memory items that I need to retrieve, then it's going to take 1,000 memory cycles to retrieve the data, but 2 memory cycles in order to give it the row and the column. That means it would take 1,002 cycles. If I was doing this with no FPM and no EDO, then it would be 3 times 1,000, which would be 3,000. So it looks like actually we're getting close. The larger blocks of data that we retrieve, or the larger blocks of memory that we retrieve, it looks that we are getting closer to being 1/3 of the amount of time it takes in order to retrieve data. All right. Now, we go back to this idea of refreshing memory. And the problem is, whenever we've got these, as we said before, whenever we're trying to store data inside of capacitors, the data slowly leaks away, both from reading and from just general time passing. So whenever the memory is not being accessed by the processor, whenever it's got a little bit of, shall we say, free time on its hands, what it will do is have just this counter that it will stop using the row address buffer as its input. And by the way, MUX is basically a switch. It allows us to switch back and forth between 2 different inputs. And so the MUX basically turns off the connection to the row address buffer, connects it to a refresh counter, and the counter just simply counts through all the rows when it has a chance, and as it's counting through the rows, 1 row at a time, it uses the refresh circuitry that's part of the column decoder in order to read a row. It just reads all the values in a row, refreshes it, and restores it to boost up the values that are currently stored in those capacitors. All right. So that's a lot of information, but we're going to do just a little bit more. Oh, and by the way, whenever it comes to the refresh circuitry, what we can use is just simply take that, what we're doing is we're just going to read the value and then route it right back around so that we can store it. And that's how the values are reboosted or refreshed in each one of those memory locations. All right. All right. One more piece of information before I shut down this particular recording. You may have heard the term SDRAM. A lot of people say, well, SDRAM, is that static dynamic RAM? No, the S in SDRAM has nothing to do with the static RAM. Remember, the static RAM is the one that's made from NAND gates, the one that's made entirely from transistors. DRAM is the RAM that is made with capacitors. So whenever you add this S in front of DRAM, that actually means synchronous. And anytime you hear the term synchronous, you need to think of this idea of a clock. Now, what a clock does for us. In the conventional RAM, the non-SD RAM, what we've got is timing. Each one of these periods or these memory cycles is actually dependent on a delay. How long the memory it requires in order to provide that. There's basically a minimum amount of time that we need to provide the row, a minimum amount of time that we need to provide the column, a minimum amount of time that the data is going to be available, or a pause, for example, that we have to wait for data to become available on our memory. Well, we can actually better or tighten up the interface between memory and the processor by synchronizing things with this clock. We were talking about, when we were introducing memory, we talked about the 3 different types of buses that come between the processor and the memory. There was the data, there was address, and there was control. And control, we talked about the R bar and the W bar. Now we also have RAS and CAS. But now we also have this clock. And this clock synchronizes things so that everything is lockstep between the processor and memory. Now, what happens here is that the processor says, I want to read some data. And the memory says, hang on a second. I need to take just a moment, because of the delays internal to the chip and so forth. I need to take just a moment in order to get the data that you want. But this is where the clock becomes incredibly important. Once I've got the data, I'm going to tell you I've got the data. And then with every clock pulse that you send me, I'm going to give you the next piece of data. Give me a clock pulse, I'll give you the next piece of data. Give me a clock pulse, I'm going to give you the next piece of data. And that is the synchronous part. There are a couple of important things here that to remember. One is that the delay is required in order to fill a buffer. This delay fills a data buffer. The memory uses that period of time in order to make it so that it can pack its buffer with all of this data that it's going to send. Once that delay has passed, then it's going to, with every clock pulse, send a piece of data. Now, after a while, the memory technology improved so that we were able to give this data back to the processor a little bit quicker. So, whenever we started doing that, the rate at which we could send data back to the processor increased, so that instead of sending just 1 piece of data per clock cycle, we actually were able to send 2 pieces of data back per clock cycle. We sent 1 piece of data for the rising edge, 1 piece of data for the falling edge, 1 piece of data for the rising edge, 1 piece of data for the falling edge. We were able to double the rate at which we were able to send data back to the processor. That is where this idea of DDR comes in, double data rate. So double data rate basically means now I'm sending you back 2 pieces of data in a single clock cycle. But there was a consequence, and the consequence was that I had to fill up more of my buffer. So this delay increased. By increasing the delay, that pushed back how much time was going to pass before the processor could expect to start getting data back. That meant that early DDR was actually not that much of an improvement over the regular SDRAM. The regular SDRAM could start sending data back sooner, although the double data rate was, once it got to the point where it could send data back, it was sending it faster. So there was a balancing act we were playing here. Some of the early DDRs were slower, in fact, than SDRAM. So DDR, once again, we have to increase the delay in order to fill more data buffer. But once we've got the buffer filled, we're then going to send data twice as fast back. Well, we went to DDR2, and DDR2 said, now what I'm going to do is I'm going to send you 4 bytes of data back in a single clock pulse. Now this, of course, took some time, some interpretation of the timing on the processor and RAM side to know exactly when, for example, the halfway point was in each one of these clock cycles. But in that case, what we were doing was sending 1, 2, 3, 4 bytes of data back in a single clock pulse, hence the DDR2. DDR3, 8 you sent back 8 bytes of data in a single clock pulse. DDR4, you're sending 16 bytes of data in a single clock pulse. But once again, every time you increase the speed at which you're sending data back, you're also increasing the delay that it takes in order to fill the buffer. Just have a little table down here of a summary of the data rates, and you can see that not only did the data rates increase, all right, we had a little bit of an increase of data rates, the physical connections were redefined between the memory and the processor, which made it so that the size of our memories were also able to increase. Another thing that's important is that the DDR memories use less power. The requirements were that they use less power. And so you'll also see this lowering of voltages. The original DDR RAM took 2.5 volts to run it. And every time you increase, or every time you wanted to decrease the power consumption, once again, power consumption is really important whenever you're talking about portable devices such as laptops or phones. In order to save power, you have to lower the voltage that drives these chips.